It came from nowhere, a whisper in the steppes, and then, like wildfire across a continent, it consumed everything. Between 1346 and 1353, the Black Death killed 50 million people. 1 out of every 3 Europeans simply ceased to exist. Kingdoms fell, the medieval world died, and from its ashes, the modern world was born. But what was it? This invisible assassin that moved faster than armies, that struck down king and peasant with equal ferocity. Tonight, you will discover the answer. We will travel back 700 years to the remote grasslands where it all began. We will decode the bacterium itself, unravel its secrets, trace its DNA through the centuries. And we will discover how this ancient enemy still lives among us today, waiting in the shadows. This is the complete science of the Black Death. Before we begin, if you enjoy these types of interesting science topics, hit the like button, comment, and tell us where you are listening from. If you'd like to hear more stories like this, you know what to do. Simply subscribe. In the high grasslands of Central Asia, where the wind moves unbroken across ancient steppe, a microscopic life form has existed for millennia. Long before cities rose, before trade routes carved through continents, before human civilization reached its medieval height, a bacterium lived quietly within the bodies of wild rodents. This organism, shaped like a tiny rod, invisible to the naked eye, would eventually reshape human history more profoundly than any army or empire. The bacterium belongs to a family of microorganisms that evolved over countless generations in the harsh ecosystems of the Eurasian interior. Here, on plateaus stretching from Mongolia to the western edges of China, populations of marmots and ground squirrels burrow into earth, creating vast underground networks. These creatures live in colonies, sometimes numbering in the thousands, their tunnels connecting beneath grasslands that appear empty to the casual observer. Within these colonies, the bacterium found its ancestral home. The pathogen exists in a delicate ecological balance. It circulates through rodent populations in cycles that rise and fall with seasons, with rainfall, with the abundance of grass and the density of animal communities. When conditions align, when populations grow dense and fleas multiply in warm months, the bacterium moves efficiently from host to host. When winter arrives or populations decline, the pathogen retreats into quieter circulation, waiting in survivors, persistent in its ecological niche. Fleas serve as the critical bridge in this ancient cycle. These tiny insects, adapted over millions of years to feed on mammalian blood, become vessels for bacterial transmission. The flea takes blood from an infected rodent, ingesting the bacterium along with its meal. Inside the flea's digestive system, the bacterium multiplies, forming dense colonies that block the insect's ability to feed properly. The hungry flea bites repeatedly, and with each bite, it regurgitates bacteria into a new host. This is the engine of circulation in the wild. For thousands of years, this system remained stable, contained within the ecological boundaries of Central Asian wildlife. The bacterium had no interest in humans, no evolutionary drive toward our species. It simply existed, adapted to its rodent hosts and flea vectors, part of the intricate web of life in remote grasslands. Human populations occasionally intersected with these cycles, particularly nomadic groups and hunters who encountered infected animals. But large-scale transmission required conditions that would not emerge until human societies underwent profound transformations. The key to understanding this disease begins here, in these windswept highlands, where ecology, climate, and microscopic life intersected long before recorded history. The bacterium was not created to afflict humanity. It was simply there, following the patterns of survival that all life follows, reproducing, spreading, persisting. What would later be called plague, what would be remembered as the Black Death, was originally just another thread in nature's vast tapestry, remarkable only for how unremarkable it was in its original context. As human societies grew more complex, as populations expanded and trade networks lengthened, as cities emerged along ancient routes connecting east and west, the stage was set for an intersection. The pathogen's journey from isolated rodent populations to global pandemic would require not just biological capability, but historical circumstance. It would require the movement of goods, the growth of urban centers, the conditions of medieval life that brought humans into sustained contact with the reservoirs where this ancient bacterium waded. The grasslands of Central Asia remain, even today, a natural home for this organism. Endemic circulation continues in wild rodent populations, a reminder that the disease did not disappear from Earth but merely withdrew from its catastrophic encounter with human civilization. Modern surveillance systems monitor these areas, understanding that the ecological conditions which gave rise to pandemic plague still exist. The bacterium persists in its ancient patterns, adapted to its original hosts, a living connection to the biological origins of one of history's most transformative diseases. This is where the story begins, not in human suffering, not in medieval cities, but in the deep evolutionary past, in the simple biological fact of a bacterium adapted to life in the digestive tracts of fleas and the blood of burrowing rodents. Everything that follows, all the history and horror, the transformation of continents and the collapse of societies, emerges from this singular ecological relationship, forged over countless generations in the remote interior of Asia. The pathway from ecological reservoir to human infection requires a series of precise biological events, each dependent on the alignment of host, vector, and environmental conditions. Understanding how plague begins means following the bacterium's journey from its natural home into human tissue, a journey facilitated by one of nature's most efficient disease vectors, the flea. The oriental rat flea, small enough to rest on the tip of a finger, has evolved specifically to feed on rodent blood. Its mouthparts pierce skin with surgical precision, reaching capillaries just beneath the surface. In its natural cycle, the flea moves between rats, mice, and other small mammals, taking blood meals necessary for reproduction. When a flea feeds on an infected rodent, it draws blood containing the plague bacterium into its digestive system. What happens next transforms the flea from simple parasite into deadly vector. Inside the flea's gut, the bacteria begin to multiply rapidly. They form dense colonies that adhere to the walls of the digestive tract, particularly in the area just before the stomach, called the proventriculus. As bacterial numbers increase, they create a living blockage, a mass of organisms so thick it prevents blood from passing through normally. The flea becomes starving, unable to properly digest its blood meals. This blockage is crucial to transmission because it turns the flea into a biological syringe, repeatedly injecting bacteria as it attempts desperately to feed. When a blocked flea bites a new host, whether rodent or human, the bacteria are forced backward into the bite wound. The flea's feeding attempt becomes a bacterial delivery system. With each bite, thousands or even millions of bacteria enter the host's skin, beginning the infection process. For humans, this moment of transmission typically occurs when infected fleas abandon dying rodent hosts and seek alternative blood sources. As rat populations in human settlements succumb to plague, their fleas jump to humans, driven by hunger and the warmth of nearby bodies. The bacteria that enter human skin through a flea bite encounter a landscape completely foreign to their evolutionary experience. Human tissue, human immune responses, human body chemistry differ significantly from the rodent hosts to which the bacterium is adapted. Yet the organism possesses remarkable versatility, carrying genetic tools that allow it to survive in diverse mammalian environments. These adaptations, refined over millennia, enable the bacterium to establish infection, even in hosts it rarely encounters in nature. Once beneath the skin, the bacteria face immediate challenge from the human immune system. White blood cells patrol tissues constantly, seeking foreign organisms. Some bacteria are captured and destroyed within hours of entry. But plague bacteria carry sophisticated defenses. Their outer surface contains molecules that interfere with immune recognition, allowing them to evade initial detection. They can survive inside immune cells that attempt to destroy them, turning predator into vehicle. This resistance buys time for bacteria to multiply and begin their migration through the body. The lymphatic system becomes the primary highway for bacterial spread. This network of vessels and nodes, designed to filter tissue fluid and mount immune responses, ironically provides plague bacteria with access to deeper tissues. From the bite site, bacteria enter nearby lymphatic vessels, carried along in fluid that normally transports immune cells and foreign material to lymph nodes for processing. The bacteria ride this current toward the nearest major lymph node, typically in the groin if the bite occurred on the leg, in the armpit if on the arm, or in the neck if on the upper body. Arrival at the lymph node marks a critical phase in infection establishment. Lymph nodes are immune organs packed with white blood cells, designed to trap and destroy pathogens. For most bacteria, reaching a lymph node means destruction. But plague bacteria possess unique capabilities that allow them not only to survive but to thrive in this hostile environment. They multiply rapidly within the node, their numbers doubling repeatedly, overwhelming local immune responses. The node swells with bacteria, dead immune cells, and inflammatory fluid, forming the characteristic bubo that gives bubonic plague its name. This entire process, from flea bite to established lymph node infection, typically requires 2 to 6 days. During this incubation period, the infected person often feels nothing. The bacteria multiply silently, building their presence before symptoms emerge. The invasion is biological, mechanical, driven by bacterial survival mechanisms that operate without intent or malice. The bacterium simply does what it has evolved to do: survive, reproduce, and spread to new hosts. That these actions cause devastating illness in humans is incidental to the organism's biological programming. The ecological bridge from rodent reservoir to human infection depends entirely on this sequence. Infected rodent, feeding flea, blocked gut, desperate biting, and skin penetration. Break any link in this chain and transmission fails. This understanding would eventually inform prevention strategies. But in the medieval world, with rats living in close proximity to humans and fleas moving freely through homes, streets, and markets, the conditions for sustained transmission were almost perfectly met. Once plague bacteria establish themselves in a lymph node, the infection enters its most dynamic phase. The disease can progress along several pathways, each determined by where bacteria spread within the body and how effectively the immune system mounts its defense. Understanding this progression means following the bacterium through human tissue, observing how a localized infection can transform into systemic catastrophe. The bubonic form represents the most common progression pattern. Within the affected lymph node, bacterial multiplication accelerates dramatically. The node, normally the size of a bean, swells to the dimensions of an egg or even larger. This expansion results from several simultaneous processes: bacterial proliferation, immune cell recruitment, inflammatory fluid accumulation, and tissue damage. The bubo becomes exquisitely painful as swelling stretches the node's capsule and presses against surrounding nerves. The overlying skin grows hot, red, and tense. Inside the bubo, a biological war unfolds. Immune cells attempt to engulf and destroy bacteria, releasing chemical signals that recruit reinforcements. Bacteria counter by producing molecules that interfere with immune function, including compounds that prevent immune cells from properly recognizing and attacking them. Some bacteria survive inside immune cells themselves, protected within the very defenders meant to destroy them. This intracellular survival allows bacteria to persist even as the immune system mobilizes aggressively. As bacterial numbers in the node reach critical levels, the infection faces a turning point. In some cases, the immune response successfully contains the bacteria within the lymph node. The infection remains localized, the bubo eventually resolves, and the patient survives, often with lasting immunity. But in many cases, particularly when bacterial load is high or immune response insufficient, bacteria break free from the lymph node and enter the bloodstream. This transition marks the beginning of septicemic plague, a far more dangerous progression. Bacteria in the bloodstream encounter a dramatically different environment. Blood flows rapidly, carrying bacteria throughout the body in minutes. The vascular system connects every organ, every tissue, providing bacteria with access to sites far from the original infection. The liver, spleen, lungs, kidneys, and bone marrow all receive blood laden with bacteria. In these organs, secondary infections establish, creating multiple sites of bacterial multiplication. The disease transforms from localized to systemic. The immune response to bacteria in blood becomes overwhelming and counterproductive. Immune cells release massive quantities of inflammatory molecules, creating what researchers describe as a cytokine storm. These molecules, beneficial in controlled amounts, become toxic when present at extreme levels. They cause blood vessels to become leaky, allowing fluid to escape into tissues. Blood pressure drops. Clotting mechanisms activate inappropriately, forming tiny clots throughout small vessels while simultaneously depleting clotting factors, leading to bleeding. This combination of widespread clotting and bleeding represents one of plague's most lethal complications. Skin changes become visible as the septicemic form progresses. Small blood vessels and extremities begin to fail. Fingers, toes, and other tissues develop dark discoloration as blood flow becomes compromised and tissue begins dying. This necrosis, combined with the purplish hue of bleeding into skin, gives plague one of its most notorious visual characteristics. The blackening of skin, particularly visible in the extremities, contributed to the medieval name Black Death, though the term also references the profound darkness of the disease's impact on society. In a particularly deadly progression, bacteria reach the lungs. When lung tissue becomes infected, pneumonic plague develops. This form introduces a new dimension to disease transmission because bacteria multiply in airways and alveoli, the tiny air sacs where oxygen exchange occurs. Infected persons develop severe coughing, bringing up fluid contaminated with massive numbers of bacteria. Each cough aerosolizes bacteria, creating infectious droplets that hang in air and can be inhaled by others nearby. Pneumonic plague thus becomes directly transmissible from person to person, bypassing the need for flea vectors entirely. Pneumonic transmission dramatically accelerates plague spread in crowded conditions. Unlike bubonic plague, which requires flea bites and typically spreads more slowly, pneumonic plague can move through households, hospitals, and crowded spaces rapidly. Incubation time shortens to 1 to 3 days. Disease progression accelerates. Without modern treatment, pneumonic plague proves almost universally fatal, killing most victims within days of symptom onset. This form represents plague at its most efficient and most deadly. Environmental and social conditions profoundly influence how plague spreads through populations. Cool, humid conditions favor flea survival and activity, making spring and autumn peak seasons for bubonic transmission. Crowded living conditions, with humans and rats in close proximity, maximize contact between infected fleas and people. Poor sanitation provides ideal habitat for rat populations to thrive. Warfare, trade, and human migration carry infected individuals and contaminated goods across distances, seeding new outbreaks in distant locations. The disease spreads not through biological mechanisms alone, but through the intersection of ecology, climate, and human behavior. The progression from a single flea bite to community-wide outbreak follows patterns that amplify exponentially. One infected person develops symptoms. Their fleas bite family members and neighbors. Those individuals develop infections. Their fleas continue the cycle. Within weeks, an isolated case becomes a neighborhood outbreak. Within months, an entire city faces epidemic. The biological speed of bacterial multiplication, combined with the efficiency of flea transmission and the vulnerability of human populations lacking immunity, creates conditions for explosive spread. This is how a bacterium adapted to Central Asian rodents became, under specific historical circumstances, one of humanity's most devastating pathogens. The transformation of plague from an endemic disease of Central Asian wildlife to a pandemic that reshaped continents required the convergence of biological, environmental, and human factors. The pathogen's global journey follows trade routes, military campaigns, and the expansion of interconnected societies, demonstrating how disease emergence depends not just on microbiology, but on the patterns of human civilization itself. The bacterium likely circulated in localized outbreaks for centuries before conditions aligned for intercontinental spread. Early historical records from various civilizations describe episodes of severe illness consistent with plague. Though definitive identification remains challenging across the distance of millennia, what seems clear is that periodic spillovers from wildlife reservoirs into human populations occurred throughout ancient history, causing local catastrophes that faded without spreading far beyond their points of origin. The first clearly documented pandemic emerged in the mid-6th century, beginning in the eastern Mediterranean and spreading through the Byzantine Empire. This outbreak, which persisted in waves for over 2 centuries, followed trade routes connecting Africa, Asia, and Europe. Ships carrying grain from Egypt to Constantinople also carried rats and their infected fleas. The disease moved along Roman road networks, through military camps, into cities and rural areas alike. Historians estimate that this early pandemic killed millions, fundamentally weakening the Byzantine Empire and altering the trajectory of Mediterranean history. After centuries of relative quiescence, plague returned to the human stage in the 14th century with unprecedented ferocity. The pandemic's origins trace to the same Central Asian highlands where the bacterium evolved. But now, the Silk Road provided a highway for global transmission. Merchants, soldiers, and travelers moving between Asia and Europe carried the disease westward. The Mongol Empire, which at its height stretched from China to Eastern Europe, inadvertently created an epidemiological superhighway, allowing plague to traverse distances that would previously have isolated outbreaks. The disease reached the Black Sea region in the late 1340s, carried by armies and traders. From there, merchant ships spread it throughout the Mediterranean. Genoese trading vessels fleeing conflict carried plague to Sicily, southern Italy, and southern France in the autumn of 1347. By the following year, the disease was moving up the Italian peninsula and spreading through southern European ports. Marseille, Barcelona, Valencia all became nodes of transmission. Ships carried plague to North Africa, where it devastated cities from Alexandria to Tunis. The pathogen moved faster than news of its approach, faster than any attempted quarantine measures. From Mediterranean ports, plague spread inland through river valleys and overland trade routes. By the summer of 1348, the disease reached Paris, moving up the Rhone River Valley and through established trading networks. It crossed the English Channel, arriving in English ports by early autumn. By winter, it was in London. The following year saw plague spread through the British Isles, reach Scandinavia, and push into Eastern Europe. By 1351, the first pandemic wave had touched nearly every corner of the European continent, from Iberia to Russia, from Sicily to Norway. The speed and completeness of this spread reflected the interconnected nature of medieval European society. Trade networks linked cities across vast distances. Pilgrimage routes brought travelers from across the continent to common destinations. War displaced populations and concentrated people in camps and besieged cities. Agricultural systems fed urban populations, creating dense settlements where disease could spread rapidly. The very achievements of medieval civilization, the trade, connectivity, and urbanization that marked human progress, created optimal conditions for pandemic disease. The death toll remains difficult to calculate with precision, but evidence suggests that between 1/3 and 1/2 of Europe's population died during the initial pandemic wave. Some regions suffered even more catastrophic losses, with certain towns and villages losing the majority of their residents. The demographic impact reshaped European society fundamentally. Labor shortages empowered workers, contributing to the erosion of feudal systems. Land values shifted. Traditional authorities, unable to stop the disease, lost credibility and power. The psychological trauma of witnessing such mortality left lasting marks on art, literature, and religious thought. Plague did not vanish after this initial wave. The bacterium established itself in European rodent populations, creating new endemic reservoirs. Periodic outbreaks recurred over the following centuries, sometimes remaining localized, other times spreading regionally. Major resurgences occurred in the early 16th century, the mid-17th century, and sporadically through the 18th century. Each outbreak reinforced plague's place in the European consciousness, a recurring threat that shaped public health practices, urban planning, and social policy. The disease also continued to affect other regions. The Middle East experienced repeated plague outbreaks through subsequent centuries. North African and Eastern Mediterranean communities faced endemic circulation. In Asia, plague persisted in its original reservoirs and caused periodic epidemics in Chinese, Indian, and Southeast Asian populations. The disease remained a global presence, not just a European catastrophe, though European documentation has tended to dominate historical narratives. A third major pandemic phase began in the mid-19th century in China's Yunnan province, where plague had likely circulated continuously in wildlife reservoirs. This outbreak followed the patterns of 19th century globalization, spreading via steamship routes to ports worldwide. The disease reached Hong Kong, then spread to India, Southeast Asia, South Africa, South America, and North America. San Francisco experienced outbreaks in the early 20th century. The disease reached Australia. For the first time, plague became truly global, present on every inhabited continent. This third pandemic also coincided with the emergence of modern microbiology. Researchers in Hong Kong and Paris independently identified the bacterium in the late 1890s, finally revealing the specific organism responsible for plague. Understanding the flea transmission cycle followed shortly thereafter. This scientific knowledge transformed plague from mysterious pestilence to understood pathogen, enabling targeted prevention and control measures that would eventually bring the disease under control, though not before millions more deaths in Asia and other affected regions. The historical geography of plague reveals how disease emergence depends on the intersection of ecological reservoirs, vector biology, and human social patterns. The bacterium remained essentially unchanged, but its impact on humanity varied enormously based on when and where spillover occurred, what trade routes existed, how densely populations lived, and what understanding and tools societies possessed to respond. The same pathogen caused catastrophe in one era and remained manageable in another, demonstrating that disease impact emerges from the relationship between organism and host population, not from the organism alone. In the contemporary era, plague persists as both historical memory and present reality. While the disease no longer causes pandemic devastation, it remains endemic in specific regions and continues to cause illness, revealing ongoing challenges in global health equity and the persistent intersection between human societies and wildlife disease reservoirs. The disease typically announces itself with sudden onset of severe symptoms. A person who was well yesterday becomes acutely ill almost overnight. Fever rises rapidly, often accompanied by chills so intense the person shakes uncontrollably. Profound weakness follows, making even simple movements exhausting. Headache pounds relentlessly. Muscle aches affect the entire body. These initial symptoms resemble many other infections, offering no immediate clue to the specific cause, delaying recognition in regions where plague is rare. Within a day or two of symptom onset, the characteristic bubo usually develops in bubonic cases. The affected lymph node, typically in the groin, armpit, or neck, swells visibly. The overlying skin becomes stretched, shiny, and discolored, often appearing red or purplish. The area feels hot to touch, reflecting intense inflammation beneath. Most dramatically, the bubo becomes exquisitely painful. Any movement that stretches or compresses the swollen node causes severe discomfort. Patients often hold the affected limb in positions that minimize pressure on the bubo, a postural adaptation that becomes characteristic of the disease. As illness progresses untreated, additional symptoms emerge. Nausea and vomiting develop, often severe enough to prevent eating or drinking. The gastrointestinal system, disrupted by bacterial toxins circulating in blood, ceases normal function. Abdominal pain may become severe. Some patients develop diarrhea, others constipation, reflecting the variable ways in which systemic illness affects different organ systems. Dehydration worsens rapidly when fever, vomiting, and inability to drink combine. When infection spreads to the bloodstream, the clinical picture darkens considerably. Blood pressure drops as vessels leak fluid into tissues. The heart races, trying to maintain circulation despite falling pressure. Breathing becomes rapid and shallow. Confusion sets in as brain perfusion decreases. Extremities turn cold as blood shunts to vital organs. Small areas of skin, particularly on fingers, toes, and nose, may turn dark purple or black as tiny clots form in capillaries and tissue dies from lack of oxygen. This dramatic skin necrosis, while not present in all cases, represents one of plague's most visually striking features. Pneumonic plague presents differently, focused on respiratory rather than lymphatic symptoms. Cough begins within a day or two of infection, initially dry but rapidly becoming productive of fluid. This fluid, tinged with blood, contains massive numbers of bacteria. Chest pain develops, sometimes severe enough to make breathing painful. Shortness of breath worsens rapidly as lung tissue becomes increasingly involved. The patient appears acutely ill, breathing rapidly, struggling for oxygen, skin taking on a bluish tint from inadequate oxygenation. Without treatment, respiratory failure follows quickly, often within 2 to 4 days of symptom onset. Modern plague distribution reveals stark geographic and economic patterns. The disease persists primarily in rural areas where wild rodent reservoirs remain active. Madagascar experiences the highest number of cases globally, with hundreds reported annually, primarily in highland regions where plague has become endemic in local rat populations. Several African nations report regular cases, particularly in East African highlands. Parts of Asia, including regions of China, Mongolia, and Central Asian countries, continue to experience sporadic cases. In the Americas, plague persists in wild rodent populations throughout the western United States and in parts of South America, causing occasional human cases when people contact infected animals or fleas. The distribution of modern plague correlates strongly with poverty and limited healthcare access. Most cases occur in rural communities where people live in close contact with rodent populations. Housing quality allows easy rodent entry, and access to medical care requires substantial travel over difficult terrain. Diagnosis often comes late because local healthcare facilities lack laboratory capacity for confirmation. Treatment, while highly effective when given promptly, requires antibiotics that may not be immediately available in remote areas. The disease thus persists primarily in populations least equipped to prevent or respond to it, a pattern common to many neglected infectious diseases. Climate and season continue to influence plague occurrence. Most cases appear during warm, humid months when flea populations peak. Heavy rainfall that increases food supply for rodents can lead to population booms, followed by increased plague transmission. Environmental changes, including land use shifts that bring humans into closer contact with wildlife, create new opportunities for spillover. Climate change may be expanding the geographic range where plague can persist, as warming temperatures allow rodent and flea populations to survive in previously inhospitable areas. Public health systems in endemic regions maintain surveillance for plague, tracking human cases, monitoring rodent populations, and testing dead animals found in residential areas. Early warning systems attempt to detect increases in rodent die-offs that might signal heightened plague activity. Public education campaigns teach communities to avoid contact with wild rodents, control rat populations around homes, use flea prevention on domestic animals, and seek rapid medical care for suspicious symptoms. These efforts reduce but do not eliminate plague's presence, as the ecological reservoirs remain intact and human-wildlife contact continues. Cultural dimensions shape how communities experience and respond to plague. In some endemic regions, traditional beliefs about disease causation compete with biomedical understanding. Stigma can attach to plague patients, based on associations between the disease and poverty or uncleanliness. Fear of the disease, rooted in its historical reputation, sometimes leads to delayed care seeking or concealment of cases. Effective public health responses must therefore address not just biological transmission but social and cultural factors that influence behavior and access to care. The contrast between plague's historical devastation and its modern controllability reveals both the power of medical advancement and the persistence of health inequity. The same disease that once killed millions now typically kills hundreds annually, and virtually all those deaths occur in impoverished communities with limited healthcare access. This pattern reflects a broader truth about infectious diseases in the modern world. They persist primarily where poverty, inadequate infrastructure, and limited access to prevention and treatment create conditions for ongoing transmission. Plague in the 21st century is less a medical mystery than a marker of global health disparities. To understand plague's devastating impact requires following the bacterium's interaction with human tissues at the cellular and molecular level, observing how a microscopic organism triggers cascading biological responses that can overwhelm even a healthy immune system. The pathophysiology unfolds as a complex dialogue between invader and defender, with the outcome determined by bacterial virulence, immune effectiveness, and timing of intervention. The journey begins in skin tissue at the flea bite site. Bacteria deposited beneath the epidermis encounter the first line of immune defense, tissue-resident immune cells called macrophages that constantly patrol for foreign organisms. These cells recognize surface molecules on bacteria as non-self and attempt to engulf them through a process called phagocytosis, essentially eating the bacteria whole. For most bacteria, this means destruction. The macrophage pulls the bacterium inside itself, enclosing it in a bubble-like compartment called a phagosome, then fuses the phagosome with packages of toxic chemicals designed to break down the invader. Plague bacteria, however, possess remarkable survival adaptations. Their outer surface contains specialized molecules that interfere with the macrophage's killing mechanisms. Instead of being destroyed, the bacteria survive inside the macrophage, protected within the very cell meant to eliminate them. More remarkably, they begin multiplying inside these immune cells, using the macrophage as both shelter and vehicle. The infected macrophage, following its normal programming, migrates through tissues toward the nearest lymph node, unknowingly carrying its bacterial cargo directly to a major immune organ. Arrival at the lymph node triggers the formation of the characteristic bubo. As bacteria multiply within macrophages and begin escaping into the node's tissue spaces, the immune system mounts a massive response. Chemical signals called cytokines and chemokines broadcast warnings throughout the immune system, recruiting additional defenders. Blood vessels in and around the node dilate, increasing blood flow and bringing more immune cells to the area. The vessel walls become more permeable, allowing fluid and cells to leave the bloodstream and enter tissue spaces. This inflammatory response causes the dramatic swelling that defines bubonic plague. Within the swelling lymph node, a battle of escalating intensity unfolds. Neutrophils, the most abundant white blood cells, arrive in massive numbers. These cells are essentially suicide warriors, releasing toxic chemicals and DNA nets designed to trap and kill bacteria, then dying in the process. Their accumulated debris, combined with dead bacteria, fluid, and dying tissue, fills the lymph node, creating pus. The node's architecture begins breaking down under the pressure of inflammation. In some cases, the node ruptures, releasing its infected contents into surrounding tissues or even onto the skin surface. The immune system simultaneously attempts a more sophisticated response. Specialized cells called dendritic cells capture bacterial fragments and present them to other immune cells called lymphocytes, essentially showing the immune system what to target. This process activates both B cells, which produce antibodies specific to plague bacteria, and T cells, which coordinate the immune attack and can directly kill infected cells. However, this adaptive response requires days to develop fully, and plague bacteria multiply so rapidly that the infection often progresses faster than adaptive immunity can effectively mobilize. If bacteria break free from the lymph node into the bloodstream, the disease becomes systemic, and the immune response becomes both more intense and more dangerous. Bacteria in blood are recognized by immune sensors throughout the body, triggering a system-wide inflammatory response. The same cytokines that help fight infection locally become problematic when released at extreme levels throughout the body. These molecules tell blood vessels everywhere to become more permeable, leading to fluid leakage from the vascular system into tissues. Blood pressure drops as the circulatory volume decreases. The heart must pump harder and faster to maintain perfusion of vital organs. Simultaneously, the blood clotting system activates inappropriately throughout small vessels. Normally, clotting occurs only at sites of vessel injury, preventing blood loss. But the inflammatory signals from systemic infection trick the clotting system into activating everywhere at once. Tiny clots form in capillaries throughout the body, particularly in extremities and organs. This widespread clotting consumes the proteins and cell fragments needed for normal clotting, leading paradoxically to increased bleeding risk. This condition, called disseminated intravascular coagulation, represents one of plague's most dangerous complications. Organs begin failing as blood flow becomes compromised. The kidneys, which filter blood continuously and require consistent perfusion, suffer damage when blood pressure drops and small clots form in renal capillaries. Kidney function deteriorates, and waste products accumulate in blood. The liver, responsible for producing clotting factors and processing toxins, becomes overwhelmed. Liver cell death releases enzymes into blood. The lungs, even when not directly infected, become affected by widespread inflammation and fluid leakage, impairing gas exchange. Oxygen levels fall. Carbon dioxide accumulates. In the brain, reduced blood flow and inflammatory molecules crossing into brain tissue cause confusion and altered consciousness. Patients become disoriented, unable to think clearly, sometimes experiencing hallucinations or seizures. This neurological involvement reflects how systemic infection affects every organ system, not through direct bacterial invasion necessarily, but through the effects of inflammation and failing circulation. When bacteria reach the lungs and establish pulmonary infection, additional pathology unfolds. Bacteria multiply in alveoli, the tiny air sacs where oxygen enters blood and carbon dioxide is expelled. The immune response fills these spaces with fluid, immune cells, and debris, preventing normal gas exchange. Areas of lung tissue become solid rather than air-filled, visible on imaging as white consolidation. Coughing becomes severe as the body attempts to clear the infected material. Each cough brings up fluid contaminated with bacteria, blood, and cellular debris. The damage extends to the lungs' blood vessels. Inflammation causes vessels to leak, further increasing fluid in air spaces. Small clots may form in pulmonary capillaries, reducing blood flow through the lungs and impairing oxygenation even in areas not directly infected. The combination of fluid-filled alveoli, impaired blood flow, and damaged tissue creates severe respiratory failure. Oxygen levels drop critically. The patient struggles to breathe, working harder and harder with less and less success. Throughout these processes, the body attempts various repair and compensation mechanisms. Blood vessels constrict in some areas to maintain pressure. The heart pumps faster to compensate for reduced volume. Breathing rate increases to bring in more oxygen. Stress hormones flood the system, mobilizing energy reserves. But these compensatory mechanisms have limits, and when those limits are exceeded, organ systems begin failing irreversibly. The outcome depends on whether medical intervention can interrupt these cascading pathological processes before damage becomes too extensive to reverse. Understanding these mechanisms reveals why plague is simultaneously so dangerous and so treatable. The bacteria multiply rapidly and trigger overwhelming immune responses, creating rapidly progressing, life-threatening illness. But the bacteria themselves remain vulnerable to antibiotics that interfere with their growth and reproduction. Early treatment, before the pathophysiological cascade becomes too advanced, can halt bacterial multiplication, allowing the immune system to clear the remaining organisms and the body to begin healing damaged tissues. The race is between bacterial proliferation and medical intervention, with timing determining outcome in many cases. Beyond the immediate crisis of acute infection, plague leaves lasting marks on individuals, families, communities, and the global health landscape. Understanding the disease's full impact requires looking beyond mortality statistics to examine the long-term consequences for those who survive, the trauma borne by affected communities, and the persistent challenges plague poses in endemic regions. Survivors of severe plague face varied long-term physical consequences. Those who experienced extensive bubo formation may carry permanent scarring in affected lymph node regions. If buboes ruptured or required surgical drainage, the resulting scars can be significant. More serious are the consequences of tissue necrosis in extremities. When fingers, toes, or other tissues died during septicemic plague, survivors may lose these body parts either through natural sloughing or surgical amputation. Such permanent physical changes affect not just function but identity and livelihood, particularly in communities where manual labor provides income. Organ damage from severe illness creates additional long-term complications. Kidneys damaged during acute infection may never fully recover, leaving survivors with chronic kidney disease requiring ongoing management. Lung tissue scarred by pneumonic plague may reduce respiratory capacity permanently, causing shortness of breath with exertion and increased vulnerability to respiratory infections. Liver damage may resolve slowly or leave lasting impairment. These organ consequences transform acute infection into chronic illness, requiring ongoing medical care that may be difficult to access in the same rural, impoverished settings where plague infection occurred. Neurological consequences can persist long after infection clears. Survivors sometimes report cognitive difficulties, memory problems, or personality changes following severe illness. These changes may result from periods of poor brain perfusion during acute illness, from direct effects of inflammation on brain tissue, or from the profound physiological stress of near-death illness. Such neurological effects, while often subtle, can affect work capacity, social relationships, and quality of life. In settings lacking neuropsychological support services, survivors must adapt to these changes without formal assistance. The psychological impact of surviving plague extends beyond direct neurological effects. Experiencing life-threatening illness creates trauma, particularly when disease progression was rapid and severe. Survivors may develop anxiety, depression, or post-traumatic stress disorder. The knowledge that one survived while others died creates survivor's guilt, especially when family members perished. Sleep disturbances, nightmares, and hypervigilance are common. In communities where mental health services are limited or stigmatized, these psychological wounds often go unaddressed, compounding over time. For families, plague creates cascading burdens, even when patients survive. The immediate costs of illness, including medical care, transportation to hospitals, and income loss during sickness, can be financially devastating for already impoverished households. When primary earners become ill, families lose income precisely when expenses increase. If patients die, families lose breadwinners permanently, plunging households into poverty and forcing children to leave school to work. The disease thus perpetuates cycles of poverty, affecting not just individuals but entire family trajectories across generations. Community-level impacts extend beyond individual cases. Plague outbreaks in small communities create collective trauma, particularly in regions where historical memory of the disease's devastating potential remains strong. Fear can disrupt normal social interactions and economic activities. Markets may empty, agricultural work may be delayed. When outbreaks occur during critical farming periods, the impact on food security can extend months beyond the outbreak itself. Community cohesion may suffer if stigma attaches to affected families or neighborhoods. Healthcare systems in endemic regions face ongoing challenges managing plague risk alongside numerous competing health priorities. Maintaining surveillance systems requires sustained investment in laboratory capacity, field epidemiologists, and rodent monitoring programs. Healthcare workers need regular training to recognize plague cases promptly, as many may go years without encountering the disease. Ensuring antibiotic availability in rural areas requires supply chain management and resources. These requirements strain already limited public health budgets, forcing difficult decisions about resource allocation. The global health community's response to plague reveals broader patterns of priority and neglect. Because the disease primarily affects poor, rural populations in limited geographic areas, it receives far less research funding and pharmaceutical industry attention than diseases affecting wealthier populations. Vaccine development has progressed slowly, despite demonstrated technical feasibility. Diagnostic tools remain less sophisticated than for diseases considered more commercially valuable. This pattern of neglect reflects how global health priorities often align more closely with economic potential than with disease burden in affected populations. Comparatively, plague occupies a unique position among infectious diseases. It causes far fewer deaths annually than diseases like tuberculosis, malaria, or HIV, yet it carries disproportionate historical weight and public consciousness. This disconnect between current burden and historical memory shapes how resources are allocated and risks are perceived. Some argue plague receives more attention than its current burden merits, while others contend that its pandemic potential justifies ongoing vigilance and investment. Both perspectives contain truth, highlighting the complexity of priority setting in global health. Endemic regions face the challenge of sustaining public attention and resources for a disease that may appear sporadically but unpredictably. Years may pass with few cases, creating pressure to redirect resources to more immediate health priorities. Then outbreaks occur, exposing gaps in preparedness. This pattern of episodic crisis and prolonged quiescence makes sustained institutional commitment difficult, leaving systems perpetually reactive rather than proactively prepared. Climate change introduces new uncertainties about plague's future distribution and burden. Warming temperatures may expand the geographic range where rodent and flea populations can support plague circulation. Changes in rainfall patterns could affect rodent population dynamics, potentially increasing spillover events. Human encroachment into wildlife habitats, driven partly by climate impacts on agriculture and habitability, may increase contact between people and infected animals. These ecological shifts could expand plague's reach or intensify transmission in already affected areas, demanding adaptive public health strategies. The persistence of plague in the modern world, despite available tools for prevention and treatment, ultimately reflects broader failures of global health equity. The disease persists, not because we lack knowledge or capability to control it, but because affected populations lack access to the resources and infrastructure that would enable control. This reality transforms plague from a purely medical problem into a manifestation of structural inequality, where disease burden falls disproportionately on those least able to prevent or address it. Solving the problem of plague, in this sense, requires addressing the deeper problems of poverty, access, and equity that allow it to persist. Plague occupies a unique space in the human narrative, functioning simultaneously as biological reality, historical force, and enduring metaphor. Understanding its full significance requires stepping back from molecular mechanisms and clinical presentations to examine how this disease has shaped, and continues to shape, human civilization in ways that extend far beyond immediate illness and death. The demographic catastrophe of 14th century plague fundamentally transformed European society. The death of between 1/3 and 1/2 of the population within a few years created labor shortages that shifted economic power dramatically. Workers, suddenly scarce, could demand higher wages and better conditions. Serfs gained mobility and negotiating power. The feudal system, dependent on abundant, cheap labor, began its long dissolution. Land values collapsed in some areas and shifted in others. Traditional social hierarchies weakened as death proved indifferent to rank and status. The disease killed peasants and nobles, clergy and merchants, scholars and laborers with equal efficiency, creating a strange democracy of mortality that undermined belief in social order as divinely ordained. Cultural production reflected and amplified plague's psychological impact. Art grew darker, more focused on mortality and the transience of life. The danse macabre, depicting death dancing with people of all social stations, became a recurring theme. Literature explored themes of divine judgment, random catastrophe, and the fragility of human existence. Religious movements intensified, some emphasizing penance and divine mercy, others questioning traditional authority when prayers failed to stop the dying. The psychological landscape of late medieval Europe was indelibly marked by collective trauma, creating cultural patterns that persisted for generations. Medicine and public health emerged partly in response to plague. Early attempts at control, such as quarantine measures implemented by Italian city-states, established precedents for state intervention in disease control. The recognition that disease could spread through human contact, even without understanding the mechanism, led to isolation practices and travel restrictions. These efforts, while often ineffective against plague, established the framework for organized public health responses that would evolve over subsequent centuries. The disease thus catalyzed the development of institutions and practices that remain foundational to modern public health. Scientific understanding of plague advanced through the intersection of medical crisis and technological capability. The identification of the bacterium in the 1890s required both microscopy and bacteriological techniques developed over the preceding decades. Understanding flea transmission demanded careful epidemiological observation and experimental verification. This work exemplifies how disease investigation drives scientific methodology, creating tools and approaches applicable far beyond the original problem. Plague research contributed foundational concepts to epidemiology, vector biology, and bacterial pathogenesis that informed disease research broadly. The disease's persistence in modern times reveals both the strengths and limitations of biomedical advancement. We understand plague's bacteriology, ecology, transmission pathways, and pathophysiology in extraordinary detail. We possess highly effective antibiotics and can develop vaccines, yet plague continues to sicken and kill, primarily in populations lacking access to these tools. This persistence demonstrates that scientific knowledge alone cannot eliminate disease when structural barriers prevent its application. The remaining burden of plague reflects global inequities more than scientific insufficiency. Contemporary plague research addresses multiple frontiers simultaneously. Scientists monitor wildlife reservoirs using genetic sequencing to track bacterial evolution and movement. They model climate impacts on rodent and flea populations, attempting to predict where plague risk may increase. They work on improved diagnostics suitable for resource-limited settings. Vaccine candidates undergo evaluation, though commercial development remains limited by small market size. This research continues not because plague poses imminent pandemic threat, but because endemic disease burden justifies intervention, and because understanding plague illuminates broader questions about disease, ecology, and emergence. The symbolic weight of plague in human consciousness exceeds its current epidemiological importance. The term plague functions as metaphor for catastrophic contagion, whether literal or figurative. Writers and speakers invoke plague when describing everything from social ills to computer viruses, drawing on its historical resonance. This metaphorical power reflects plague's unique status as a disease that fundamentally shaped human history, creating a cultural reference point that transcends its specific biological reality. The Black Death lives in collective memory in ways that few other diseases do. Plague's pandemic potential, while currently low, cannot be dismissed entirely. The bacterium retains its virulence. Wildlife reservoirs remain extensive. Climate change and ecological disruption create opportunities for increased spillover. Most concerning, pneumonic plague's capacity for direct person-to-person transmission means that under specific circumstances, rapid spread remains theoretically possible. Modern antibiotic resistance in plague bacteria, while still rare, has been documented. These factors justify ongoing surveillance and preparedness, even as they complicate risk communication that must balance vigilance with avoiding disproportionate alarm. The disease also serves as historical lens through which to examine other pandemics. Comparing plague with influenza, HIV, or more recently, coronavirus, reveals common patterns. How disease emerges from ecological disruption, how it spreads along human connection networks, how societies respond with varying combinations of denial, panic, scapegoating, and organized response. These comparisons suggest that pandemic response patterns reflect human social dynamics as much as disease characteristics. Understanding plague's history thus illuminates contemporary pandemic challenges, offering both cautionary tales and potential lessons. Looking forward, plague's future trajectory depends on choices human societies make about resource allocation, health equity, and ecological stewardship. The disease could be eliminated from human populations through sustained investment in vector control, surveillance, rapid treatment, and vaccination in endemic regions. The required tools exist. What's lacking is political will and resource commitment proportional to the burden borne by affected communities. Whether plague persists or disappears depends less on scientific capability than on collective choices about global health priorities and equity. The story of plague ultimately circles back to its origins in the grasslands of Central Asia, where the bacterium still circulates in wild rodent populations, as it has for millennia. The same ecological relationships that gave rise to pandemic disease remain intact. Fleas still transmit bacteria between animals. Occasional spillover into humans continues. The biological fundamentals haven't changed. What has changed is human understanding, capability, and, in some settings, the infrastructure to prevent spillover and treat infection promptly when it occurs. This continuity between deep past and present future represents plague's most profound lesson. Diseases do not disappear simply because we understand them scientifically or can treat them medically. They persist in the ecological and social conditions that enable their circulation. Addressing disease requires addressing these underlying conditions: the poverty that concentrates people with poor housing near wildlife reservoirs, the infrastructure gaps that delay diagnosis and treatment, the inequities that leave some populations vulnerable while others remain protected. Plague persists as biological presence and historical memory, a reminder that disease exists at the intersection of microbiology, ecology, and human social organization. The bacterium remains in the grasslands, cycling through rodent populations, carried by fleas, occasionally crossing into human lives. It follows ancient patterns, responding to ecological conditions, multiplying when given the opportunity, persisting through seasons and years. It has no intention, no malevolence, no awareness of the history it has shaped. It simply does what life does: persist, reproduce, adapt. That this microscopic organism reshaped human civilization reveals less about the bacterium than about humanity's vulnerability, resilience, and capacity for both understanding and transformation in the face of natural forces that care nothing for human concerns, but to which human fate remains intimately connected.